Welcome to the next session on machine learning using Python. So this session is we are going to talk in detail about a gradient descent methodology. So it's a method which is very much important yet interesting topic to be understood before proceeding with the next set of algorithms. So the following will be the takeaway of this session. We'll try to understand what gradient means and what descent means, and the combination of these two terms, gradient descent means to us, followed by, in contradiction to that, what gradient ascent means and why these terms are much more important in machine learning. So that's what we are going to understand through this lecture, right? Before getting into technical stuff, let me take you through a small scenario which will normally happen between a student and a teacher, right? So if not the college level, let us assume there is a student who is going to a teacher for getting trained to score high marks in his examination. High marks, what I mean by is 100 percentage. Okay. So how this assessment, how the performance of the student will be measured? Yes, of course, it is through the exams or the assessment, right? So a student will give n number of attempts starting from the first, second, three, and it goes on. And I am going to plot a graph between this attempts. Attempts is the number of times the student is writing the exam. So between this attempts and the difference in the marks, right? What is the difference? Suppose if a student is getting 95 marks, so the difference would be 5. Okay, because our expectation is to make the student to get 100 marks, right? So now if the student is getting 75 marks, the difference will be 25, and difference from the 100 percentage when he is giving his first attempt, second attempt, and it goes on, right? So for example, the student is writing an exam, and suppose this is the difference that we are getting. Let's say if he is getting 90 marks, for example. Okay, so what the teacher will do, by looking at the marks, the teacher will try to understand that his learning pace is much more slow, and hence in order to make him reach that 100 marks, some more effort has to be given or extra knowledge has to be given, right? So how this comes? It is through the understanding of how much difference. Let's say if the student has given 50 percentage, scored 50 percentage, okay, so the much more effort has to be given. If the student has scored 90 percentage, okay, the level of effort that you want to give when the student is securing 50% and the 90% will obviously vary. Okay. Now, after the teacher gives a special training to the student, okay, so then again he will make him to write an exam. This time we will expect a reduction, okay, in the difference. Means there should be a considerable improvement in the performance of the student. So, and it's obvious that the difference will go down, okay. So coming to third attempt, now also we are not able to reach the 100%. The teacher is giving much more training, okay. So based on the areas in which the student is not good at, okay. So after this training, so let us say he is getting this much difference, okay. Now the teacher could able to see a considerable reduction in the difference, meaning that his performance has gone up, okay. So what the teacher will understand, the learning pace is correct, okay. So the type of material that the teacher is giving to the students is good, and hence there is an obvious reduction in the difference, okay. This difference is what we call as the error in machine learning, right? So this process will go on, and if you look at initially when the error is much more, okay, we will try to give lot of materials and lot of information to the student, lot of training to the student to make him reduce his error to a considerable extent. For example, from 90 marks we may want to get it to 95 or 96, okay. So there the steep of your reduction may be more, or the step which you are taking, okay, to make the student perform well would be much more. But as and when you are near to your border, for example, if the student has now secured 95, 8.5, the teacher no need to put too much of effort, okay. So the amount of effort that the teacher has to put can be somewhat low, very low, and the steps taken can be somewhat be reduced compared to your previous experience, right? So and hence if you move on, we can see a considerable improvement in the student's performance, and it goes on till a point, okay. So if he has secured 99.5, okay, and even if you are stressing him again and again to get 100 percentage, most of the time it will go as a failure, and after that the attempts will go, after that the attempts will go wrong, and you could see a considerable increase in the difference, meaning that we are trying to overstress the student, and hence this is going on, right? So this point, okay, so which is the maximum efficiency that can be exerted by a student based on the training that the teacher will give, is what we call as the local minimum, right? So this is the minimal point with respect to that particular student, not with respect to the general group. This is for that particular student. That's where we call it as local minimum. Okay, for example, if the teacher has 60 students, let's assume, and if all the 60 students local minimum are being found, okay, then the minimum among all those will be the global minimum. Okay, so that's where the local minimum and global minimum comes into picture. Now, with this, we will try to understand what a gradient means to us. What is a gradient now? It's very simple. So as you move down, okay, what is the difference in y, which is called as a dy? Dy is the difference in the y direction, right? So between 2 points on space, what is the difference in y direction divided by the difference in x direction? So this is the ratio between difference in y to difference in x. Okay. In generally in physics or chemistry or in mechanics, we used to say as dt by dx. Same thing here, it is dy by dx. Change in slope, okay, with respect to your change in your dependent variable is what we call as your gradient. Okay. So having understood this gradient, next terminology we should understand is about your descent. Okay. So as we already have discussed, as and when the attempts get increased, we can see a considerable reduction in the difference or in the error. Okay, so this difference is what we call as the error, right? So and hence we could see a descending order, okay, in the difference that we have calculated. You could see, right? So this is what we call as descent. Descent in simple terms, it is the descending order. That is, we should have, if we arrange all the error items, we should be able to see a descending order among the error rates. Okay. And now combining these two, what is gradient descent? Okay, so we want a descending order in the difference of y when there is an unit increase in x. X will obviously increase, right? Because the number of attempts will obviously increase. As and when there is an increase in x, the change in y has to be reduced. Okay, that's what we call it as gradient descent. Okay. So gradual decrease in y, that's what we are in need of so as to obtain your local minima. Okay. In contrast to this, what is gradient ascent? Okay. So just you look at if this curve, okay, is rotated 180 degree, how will this look like? So this center point will go to the top, right? So that is what we call it as gradient ascent. In optimization terminologies, there are two important concepts. One is maximization, another one is minimization. The previous technique that we have seen is minimization. We should be able to obtain the local minima or global minima. The other concept is global optimization, that is global maxima, right? So for example, instead of going for error, if I want to say, I want to identify the point in which the student is securing more marks. Okay, that's where we call it as max gradient ascent. Okay, so this will happen when there is a gradual increase in y and to reach your local maxima. Okay, the local maxima is the point where the performance of the particular student is in peak. After that, his performance will go down. Okay. So what is required now, right? So in order for this particular concept to understand or how this performance will go. Okay. Now having understood what gradient is, what descent is, what gradient descent is. Now in order for making a particular student to move from one position. So assume the student performance is being assessed and he is in this position now. Now I want to improve this student performance and I want to make him attain this position. Now what are all the points that we should take care of? Okay. So what are all the points now? We first have to understand what is the deviation. What is the deviation? It is nothing but the difference from the actual requirement. Actual requirement is 100. What you have got is now only 90. The difference between these two is what we call as your deviation, right? Once the deviation is understood, okay, the teacher has to make the list of once the deviation has been understood, the teacher should know, okay, the learning pace which the student can take in order for improvement. Okay, this learning pace is very important because you cannot make a student to get very good marks by any kind of learning pace, right? So you cannot insist him to study 24 cross 7 or 10 hours a day or to write 100 assignments, right? It depends. Given your data set, what is a data set here? It is nothing but your student. So depending on the characteristics and the output you have currently at your hand, this learning pace will vary. Okay, and hence that needs to be clearly understood by the teacher. Okay, and hence the very important thing is the subject. Okay, so the teacher should know in which subject this deviation has actually happened, because the student may be having 5 or 6 subjects running at parallelly at hand, and hence this subject, which subject the student is attempting, has to be clearly understood. Okay, so when we try to match this technically, this deviation is nothing but your y dash minus yi. What is y dash I? It is nothing but your predicted output. Okay, minus yi. What is your actual output? It is yi. So the difference between your predicted and actual output is what we call as your deviation. Right. Learning pace is what we call it as learning rate. It is nothing but the amount of step that you can take. For example, when you are running down on a hill, okay, initially when you are on the top of the hill, you can take very big steps, right? But when the steep gets lower, okay, so if you take very big steps, you always get the possibility of bouncing back, okay, or else you don't know, because as and when you are approaching near that particular flat surface, we don't know how it will look like, and hence the step has to be very minimal. Okay, similar to that, if you are training a student, the same case, right? We don't know how the performance of the student is, and hence you can start teaching him in an explanatory way initially, but after once he is attaining his better performance, the teacher has to reduce, okay, his teaching methodology to make the student better achieve by himself. That's what we call it as learning rate. And this subject is what we call as the attribute, because we know when we are trying to create a data set y is equal to mx plus c, if we want to calculate, where y being your dependent attribute and x being your independent attribute, x is what we call as the attribute. So in this case we call it as the subject of interest. Okay, and normally this the table will look like this. It will be looking like a table with one input attribute and one output attribute. The subject marks becomes your input attribute, deviation becomes your output attribute. Okay, but it's a fact that only one subject will not always be there, and hence we'll have multiple subjects, right? If multiple subjects are there, let's say for example this diagram shows you have two subject marks and the deviation. Okay, how will you obtain this deviation? You have to find the deviation in each and every subject, of sum it up, find the mean, that becomes your final deviation, right? So in which case here you will have the same kind of difference learning rate, and for subject 1, subject 2, subject 3, and then subject 4, right? So if you have 4 different subjects, it's again, you understand the case here. Okay, if you have 4 different subjects, is it the importance that you need to give for improving yourself for one subject? Is it same for all other subjects? Definitely not, right? So I may be good in maths and I have secured good. I may be understanding chemistry and I may get a very lesser marks. Okay, depending on my deviation in that corresponding attribute, I have to increase the weightage, right? So the weightage has to be given according to the difference that I have on a particular subject, and hence this weights will vary for different subject. Okay, for subject 1 it may be W1, W2 for subject 2, W3 for subject 3, and W4 for subject. And hence, what's our motto now? We have to adjust the weights to get the best output. Am I right? So just quickly you see this diagram. These are the weights. Weights are nothing but the importance that you want to give to the subject. You have to come at an optimized decision by varying these weights so that the cumulative output. What is our cumulative output? The final marks that we are going to get when the deviation is being computed. We need to have our own local minima achieved. Okay, for deviation it should be local minima, but in general case it should be a performance attainment. Okay, so the performance should be the best. And hence, this is what we need to do. We have to adjust the weights to get the best possible output solution that we can get. So we'll try to map whatever we have seen to the regression function, right? Now, what is the predictor function now? Y is equal to mx plus c. Y dash I have written because it is the predicted output, right? The cost will be calculated by using the mean square error, y dash minus y, that is predicted value minus actual value, the whole squared. We have to sum up for all the attributes that we have, take its mean, and when I expand y dash of I, it will go like this, right? Just I have substituted the value of y dash, which is mx plus c, in this equation. What is our intention? The error should be equal to 0. So what are the parameters that are there existing here? If you look at, can we change xi and yi? No, right? Both are coming from the data set. Xi is your independent variable and hence it should be assumed as a constant. You cannot change. Yi is the actual output. Again, you cannot change. The only possibility to get a better output, to make the mean square error to bring down to 0, is to vary the values of m and c. Okay, and hence if you partially differentiate this equation with respect to m and c. Okay, first I am partially differentiating with respect to m. If you partially differentiate x squared, if it is, so it will become 2x, and hence 2 into the same equation y dash of I minus yi. Again we need to partially differentiate this inner part. M is mxi plus c, right? Again we need to partially differentiate this subsection mxi plus c. C is a constant, hence it will be 0, and when you differentiate it with respect to m, so it will return xi, and hence is the output. Similarly, if you partially differentiate with respect to c, the same output, but mxi term will be 0 and the value of c will be equal to 1. Okay, and hence how to modify the weights now. Okay, so our intention is to make dy dash divided by dm and dy dash divided by d dou c to 0. The difference has to be 0. Okay, 0 if we cannot obtain, but a near optimal is what is expected as a result. And hence gradient descent. What is gradient descent? You have to reduce the error when you are moving from one iteration to another iteration by increasing the performance. Okay, how to? So in order to do so, there is a possibility to change m and c only. How to do? M initial value onto your left, to the left hand side of equal to, that is the new value of m. On to the right, it is old value of m. So with my previous slope, okay, I'll try to reduce alpha, the multiplicative component or the product of three different values. Alpha, what is alpha? It is nothing but the learning pace. Okay, so I'll just quickly show you how these things came into practice. These three values came from here. Okay, So this learning rate is what we call as alpha, and attribute what we call as xi. Okay, and this we'll take as such. Okay, now if you see this formula, now if you see this formula, you can understand what is alpha. Alpha is nothing but your learning rate. Xi is the corresponding attribute. If you have 4 subjects at your hand, this needs to be repeated for every subject, because the coefficient varies for every attribute. Okay, if you have 5 attributes, then attribute 1, attribute 2, attribute 3, everything will have differing weights, and hence this formula has to be applied for all the different attributes, right? Yi dash minus yi is what we call as your the difference, right? So this is predicted output and this is your actual output. Okay, similarly the intercept has to be changed by c is equal to c minus alpha into the difference. Okay, why xi has not come? Because it's not any attribute associated with that, it's the common slope that we feel, okay, to be there in the data. So this is about your gradient descent. Hope you will understand. Okay, so in simple, to summarize in simple terms, it is nothing but a concept through which you can make the error that happened in a system to reach its local minima. Why we call it as local minima instead of zero? Because it's not at all possible to get zero in most of the real-time applications, and hence it is local minima. Example, we will try to see one workout example for better understanding. Thank you.